Good morning, students. This is Chandra Hridayve, working as Assistant Professor in Department of Mechanical Engineering. In this session, we are discussing about the problems on the crankshaft. This is the continuation problem which we have discussed in the last class. In the last class, we have discussed about the design problem of crankshaft. Once we will revise. This is the problem of the crankshaft. Design a side crankshaft for 500 mm into 600 mm gas engine. The weight of the flywheel is 80 kilonewton and explosion pressure is 2.5 megapascal. The gas pressure at the maximum torque is 0.9 megapascal. When the crank is 30 degrees from the inlet center, the connecting rod is 4.5 times the crank radius. We have write down the given data. They had given the cylinder bore D, length L. We find out the crank radius R is equal to L by 2, flywheel weight, pressure, and also the maximum torque across the pressure. P dash is equal to 0.9. Next, crank angle at which maximum torque across angle theta is equal to 30 degrees. Ratio L by R is equal to 4.5. Okay, we find out the design of crankshaft when the crank is at dead center. What we find out? We find out the load. Load FP is equal to 5 by 4 is current because pressure is equal to load by area. Then automatically force is equal to force or load. We can keep anything. Then force is equal to pressure into area. 5 by 4 into d square into P. We will find out the force of the piston. Next, first one we should find out the design of crank pin. Design of the crank pin, we will find out the force of the crank pin. FC is equal to DC into LC into PB. Okay, directly you will find out the diameter of the crank pin. Like that you will find out the length. Okay, and next you will find out the bending moment at the crank pin. M is equal to 3 by 4 into FP into LC. After that you will find out the section modulus Z is equal to 5 by 32 into DC2. Bending stress M is by Z. Okay, next we will find out the design of bearing. Then design of bearing, thickness of the crank T is equal to 0.6 into DC. Like that you will find out the length of the bearing. Next you will find out the moment, bending moment at the center of the bearing. Uh, Next you will find out the design of crank. Third step is nothing but design of crank. We will find out the design of crank wave. First you will find out the bending moment on the crank wave. M is equal to Fp into 0.75 Lc plus 0.5 T. You will find out next you will find out the direct compressive stress. Direct compressive stress and you will find out the total stress on the crank wave. Sigma T is equal to sigma A plus sigma D. Okay. Next, after that you will find out the diameter design of shaft under the flywheel. In the design of the shaft, you will find out the depending upon the reactions of the crankshaft. How you will find out the reactions? You will find out the B is equal to 250 plus L1 by L2 plus L2 by L2 by 2 plus clearance. Like that, you will find out the horizontal reaction at bearing 1 and horizontal reactions at the bearing 2. Automatically you will find the vertical reactions at bearing 1 and 2. Next you will find out the total horizontal bending moment with respect to the resultant bending moment. Mr is equal to mh square plus mv square. Next, after find out in the first step, procedure, next you should find out the design of crankshaft when the crank is at an angle of maximum twisting moment. Already we have discussed maximum twisting moment is nothing but we will find out only in the overhang crankshaft. Okay, overhang crankshaft is nothing but where the crankshaft is at the side portion of the crankshaft. When the load is applied at the side, it is called it as a side of the overhang of the crankshaft. Okay, next design of crankshaft when the crank is at an angle of maximum twisting moment. Maximum twisting moment is nothing but piston gas load. Piston gas load is nothing but Fp is equal to, or we know that 5 by 4 d square into, we will take here P dash. Okay, P dash is nothing but 500. Substitute the values, we will get the force of the piston. Next, you will find out the thrust in the connecting rod. Thrust in the connecting rod is nothing but we will find depending upon the force applying on the direction. Either it is in the thrust or in the radial positions of the connecting rod. Like that, you will write that thrust in the connecting rod is nothing but FQ is equal to FP by cos pi. Then FQ we can write it as sin pi. Sin pi is equal to sin theta by L by R. Substitute all the values, you will get the pi value. Pi is equal to 6.379 degrees. Like that, substitute the pi value in that equation. FQ is equal to FP by cos pi. FP is nothing but already we have know that 17671.4.5 by cos pi value. Substitute, you will get the FQ. Next, you will find out the tangential force applying on the crankshaft. Tangential force is nothing but Fr is equal to FQ into sin theta plus pi. Substitute all the values, you will get the Ft, tangential force acting on the crankshaft. Next, after the tangential force, you will find out the radial force. Radial force is nothing but Fr is equal to Fq cos theta plus pi. Fr is equal to, substitute all the values, you will get the Fr value. Fr is equal to 143.16 into 10 cube Newton. Next, due to tangential force Ft, the horizontal reactions at bearing 1. Horizontal reactions is the tangential force at the horizontal reaction Ht1 is equal to Ft into A plus B by B. Ht1 is equal to 105.46 into 10 cube into 509 plus 470 by 470. Like that, you will find out the horizontal tangential force reactions. Okay, the horizontal reactions at the bearing 2 also you can find out the same angle. Okay, due to the radial force Fr, the horizontal reactions at bearing 1. Horizontal reaction, you will take it as Fr into A plus B into B, A plus B by B. Next, HR1, you will take it as 292.12 into 10 cube Newton. The horizontal reaction at bearing 2. Horizontal and bearing 2 also you can write it as HRT is equal to Fr into A by B. Okay, then HRT is equal to 1.55 into 10 cube Newton. Next, first one you should find out the design of crank paper. How you will take the design of crank paper? Bending moment due to the tangential force MBT is equal to Ft into R minus D1 by 2. You will find out the bending moment of the tangential force. Like that, you will find out the bending stresses. Bending stress is nothing but we know that M by Z. Section modulus is nothing but rectangular section modulus. We can write it as 6 pi by W square T. Then sigma T tan basic stress a tangential force is nothing but you will get it as 1.768 Newton per mm square. Bending moment due to radial force. Radial force is nothing but we can take it as MB into R. MB into R is nothing but we can write it as F1 into F1 means force of the piston. Fp into 0.75 LC plus 0.5 T. You can find it out bending moment due to the radial force 32 into 10 to the power of 6 Newton per mm. Next, calculate the bending stress due to radial force. Bending stress due to radial force is nothing but you can write it as sigma BR. Sigma BR is equal to formula M by Z. We can take it as Z is nothing but rectangular modulus 1 by 6 W T square. You can write it as 6M by W T square. Substitute all the values, you will get the sigma BR means bending stress due to radial force. Next, direct compressive stress. Direct compressive stress is nothing but sigma dt is equal to Fr by Wt. Now substitute all the values, you will get the direct compressive stress. Next, total or maximum stress. Total or maximum stress is nothing but sigma max is equal to sigma c by 2 plus half into root of sigma c whole square plus 4 tau square. Okay, you will get the maximum stress. Okay, then 22.80. Since the stress is less than the permissible stress of 60 Newton per mm square, Therefore, the design is safe. We can go to the next procedure. Design of shaft under the flywheel. Design of shaft under the flywheel is nothing but let D1 is nothing but diameter of shaft under the flywheel. Horizontal bending moment acting on the shaft due to the piston gas load. MH is equal to FP into A plus B into T. Okay, minus root of HR1 square minus HT1 square. Substitute all the values, you will get the MH. MH is equal to 44.452 into 10 to the power of 6 Newton per mm. Okay, after that you will find out the vertical bending moment due to the flywheel weight. Vertical moment, bending moment is nothing but MB is equal to W B1 B2 by B. MB is equal to 9.4 into 10 to the power of 6 Newton per mm. Resultant bending moment. Resultant bending moment is nothing but MR is equal to MH square plus MB square. You will get the resultant bending moment. Next, twisting moment. Twisting moment is nothing but T is equal to Ft into R. Then you will calculate the twisting moment. Equivalent twisting moment is nothing but Te is equal to Mr square plus T square. Then you will get the equivalent twisting moment. Okay. Also, Te is nothing but 5 by 16 ds cube into tau. You are now substitute all the values. Equivalent twisting moment is equal to 5 by 16 into ds cube into 8.694. Okay, then you will get the diameter of the shaft. Okay, 390 mm. The value of ds is less than the d1. Therefore, consider ds is equal to 390 mm. Next, let ds1 is nothing but diameter of shaft at the junction of crank. Bending moment at the junction of crank M is equal to Fq into 0.75 Lc plus T. M is equal to, we know that 52.953 into 10 to the power of 6. We can write it as M is equal to 53 into 10 to the power of 6 Newton per mm. Next, twisting moment. Twisting moment T is equal to Ft into R. T is equal to 1.5.46 into 10 cube into 300. And then T is equal to 31.6 into 10 to the power of 6 Newton per mm. Equivalent twisting moment. As usual, we know that root of x square plus y square. Write that m square plus t square. Equivalent twisting moment Te is equal to root of m square plus t square will be 61.724 into 10 to the power of 6. But equivalent twisting moment Ts is equal to 5 by 16 into ds whole cube into tau. You will substitute all the values, you will get the tau is equal to 7.395 Newton per mm square. Since the induced shear stress is less than the permissible stress of 30 Newton per mm square to 40 Newton per mm square, the design is safe process which we can use in the unsafe engines. This is the problem which we have discussed in the in this session. Okay, from the first onwards, we will once revise what we have taught in the last previous classes. Okay, we are learning about the crankshaft, the design process of the crankshaft. That's why we should know what is meant by crankshaft. What is crankshaft? Crankshaft is nothing but it is a shaft which transmits the power developed by the engine to the various parts of the vehicle. It is a link between the input and output of the vehicle. Without crankshaft, our vehicle won't even move an inch through, and through our engine will be running. This is the types of crankshaft in same plane and also cross plane, and also the different types of crankshaft will be induced in this IC engines. First one, single throw crankshaft, double throw crankshaft, four throw and six throw. Okay, the functions of crankshaft. The function of crankshaft is nothing but the change is reciprocating motion of piston into rotating motion to drive propeller. Constructed of chrome, nickel, molybdenum and steel. The propeller is mounted at the front of crankshaft using a spline taper or flange. Crankshaft rotates within the crankcase and is supported by main bearing journals. This is the various parts of crankshaft which are injected onto the crankshaft. The mount on the crankshaft sprocket, counterweight, crankpin journals, crankpin oil hole, main journals, and also the flywheel of the connecting shaft. Okay, next web. Web is nothing but the portion of a crank between the crankpin and the shaft, or between adjacent crankpins called also crank arm or crank throat. Okay, next crank journals. Crank journals is nothing but in a reciprocating engine. The crank pins, also known as crank journals, are the journals of the big end bearings at the ends of connecting rods opposite to the piston. If the engine has a crankshaft, then the crank pins are the journals of the off-center bearing of the crankshaft. In a beam engine, the single crankpin is mounted on the flywheel. In a steam locomotive, the crankpins are often mounted directly on the driving wheels. Main bearings. Main bearings is nothing but in a piston engine, the main bearings are the bearing on which the crankshaft rotates, usually plain or journal bearings. The bearing hold the crankshaft in place and prevent the forces created by the piston and transmitted to the crankshaft by the connecting rods from dislodging the crankshaft, instead forcing the crank to convert the reciprocating movement into rotation. Okay, this is the simple way we are taking in the IC engines. This is the piston pin where the piston is connected to the connecting rod, and also it is joined to the crankshaft, and where the crankshaft is distributed the power throughout the engine, like that the crank pin and also the joint pin connecting the top and the bottom ring are also the different types of rings which will be induced in the IC engines. Okay, next, the overhanging crankshaft. The overhanging crankshaft is nothing but it is subjected to bending stress, direct compressive stress, shear stress, bending stress due to tangential force, bending stress due to radial force, and compressive force, compressive stresses. Okay. While designing an overhanging crankshaft, the following two steps are considered. One, when the crank is at dead center. Second, when the crank is at an angle of maximum twisting moment. Okay. These are the two types of crankshafts of which we will be taken. One is side crankshaft, another one is center crankshaft. Design procedure of crankshaft. The procedure adopted for designing a crankshaft is as follows. Initially, the magnitude of various loads on the crankshaft should be determined. The distance between the supports and their positions with respect to the load is determined. For safety and simplicity purpose, consider the shaft to be supported at the centers of the bearings. Assume the thickness of the web to be 0.4 ds to 0.6 ds, where ds is the shaft diameter or 0.22 d to 0.32 d, where d is the bore of cylinder. Calculate the distances between the supports. Finally, determine the main dimensions of the crankshaft by assuming allowable bending and the shear stress. Next, crank and crank arm. A simple form of crank is shown in the figure. It consists of an arm enlarged into a gauze at each end. The larger gauze is balanced onto the shaft, and the smaller gauze holds the pin, which is pressed into place and riveted or fastened by a nut. The empirical proportions are given in the figure 2 in terms of diameter of the shaft and diameter of the crank pin. The crank pin is usually designed as a journal and then checked for strength. Let P is equal to maximum force on the pin, P allowable bearing pressure in kg per centimeter square, L length of crank pin, D diameter of the crank pin. The different stresses induced in the crank pin is nothing but the bending stress and torsional shear stress. Okay, bending stress is nothing but sigma B is equal to mb into y by I. mb is nothing but applied bending moment. I is nothing but moment of inertia. Okay, when the beam is subjected to bending moment, and the distribution of stresses can be analyzed by bending as thick leather belt. The bending stress induced is compressive in plane. Therefore, the outer fiber is in tension and the inner fiber will always from the neutral axis. The stress induced, next one is torsional shear stress. Torsional means where the stress induced under torsion is called torsional shear stress. The torsional is said to occur when a machine member is subjected to equal and opposite couples acting in parallel planes. When a shaft is subjected to torque T, then the shear stress induced will be magnitude varying from 0 to the center. Shear stress at outer surface is given by tau max is equal to 16 T by pi d cube. Tau max is nothing but 16 T d naught pi into d naught power 4 minus di power 4. D naught is nothing but outer diameter of the shaft, Ti inner diameter of the shaft, T torque applied to the shaft. Okay. The design process of overhang crankshaft. When the crank is at dead center, the forces acting on the crankshaft is first one. The force on piston Fp, weight of flywheel, horizontal load due to the build tensions P1 plus P2. These are the three images which we are seeing, and with the supportive reactions B and C for vertical direction reactions, and also for horizontal reaction we are taking this P1 plus P2 with the distance of C1 and also the C2. By this only the reactions would be considered throughout the problems, the design process. Okay, support reaction. Support reactions is nothing but forces on piston Fp is equal to pi by 4 d square into P max. Considering forces Fp, taking moment of forces about bearing 2, Fp into B plus C is equal to R1 into V is into C. Similarly, taking moment of forces about bearing 1, Fp into B is equal to R2 into V into C. Like that, you will consider the vertical reactions. Considering forces W taking moment of forces about 1 and 2, the vertical reactions is nothing but W into C1 by C. Vertical reactions W into C2 by C. Okay, next, considering the belt could be P1 plus P2, taking moment forces about bearing 1 and 2, R2 dash H is equal to P1 plus P2 into C1 by C. Like that, you should consider both in R1 dash and also the R2 dash. Next, various process, design process considering of crankshaft. First one, design of crank pin. Crank pin is nothing but the bending moment at bearing 1 is given by PB is equal to Fp by LC into DC. Fp is nothing but forces acting on the pin. LC is nothing but length of the crank pin. DC diameter of the crank pin. PB bearing pressure of the crank pin. We will find out the L by D ratio of the crank pin 0.6 to 1.5. Next, the crank pin acts as a cantilever if load Fp is assumed as uniformly distributed. Maximum bending moment will be Fp into Lc by 2. If load is assumed to act at the end of the crank pin, the maximum bending moment is Fp into Lc. Like that, you should find out the design of bearing. The design of bearing, these bearing will be identical, and also the MB is equal to Fp into 0.75 Lc plus T plus 0.5 L1, where L1 is nothing but the length of the bearing. L1 is nothing but we can take it as 1.5 DC to 2 DC. Like that, you will find out the thickness of the web. Thickness of the web is nothing but 0.45 DC plus 0.75 DC. Same procedure is same for all the problems. Purchase the data book. If you purchase the data book, you need not to practice the procedure of the design process of the any method. Okay, directly they will give in the data book. You can keep the data book and directly you can use the step by step problems which you are considering in the problems. Okay, don't be tensed this much of design processes. There is so much problem heavy is left. You need not to fear. You can buy the design data book and the problem will be in the directly in the data book. Okay. Next, you should find out the design of crank web. Design of crank web is nothing but the crank web is subjected to eccentric load Fp. Two types of stresses are developed. One is a direct compressive stress Another one, direct compressive stress. Another one is bending stress. Direct compressive stress sigma dc is equal to Fp by W into T. W is equal to 1.14 dc. W is equal to width of rib. P is equal to thickness of rib. Next, bending moment at the center plane is given as MB is equal to FP into 0.75 LC plus D by 2. Since Z is equal to 1 by 6 W per rectangular section modulus, you can find out the total compressive stress. Like that, you find out the design of a shaft and a flywheel. It will be calculated. After that, for the maximum torque, the piston pin and also the crankshaft directly with the overhang crankshaft, you can find out the reactions with the vertical and also the horizontal reactions. Reactions of radial force Fr. Taking moment of forces about bearing to Fr into B plus C is equal to R1 dash into C. R1 dash is equal to Fr into B plus C by C. You will calculate the vertical reactions and also the horizontal reactions in the plane. After that, you should find out the user of design of Franklin. Design of Franklin is nothing but assume that Ft and Fr act at a distance of 0.5 LC from crank whip. The crank pin acts as a cantilever bending moment. The bending moment in vertical plane MBB is equal to Fr into 0.75 into LC. Okay, next we see that the problem on crankshaft. The problem on crankshaft. The problem on crankshaft is same. You can find out the procedure which we had discussed in the design process. You will find out the crank pin at the dead center. Okay, you will find out the design of crank pin. Next, you can find out the design of bearing, and you can find out the design of crank whip. Okay, same like that only, and also you can find out the maximum torque applied in the procedure.